So today we are glad to have Dr. Bai from Washington University in St. Louis to give a talk on spatiotemporal heterogeneity in battery electrodes. A little bit of introduction of Dr. Bai. He obtained his bachelor's degree in automotive engineering and PhD degree in mechanical engineering from Tsinghua University in 2007 and 2012, respectively. He continued his research in Department of Chemical Engineering at MIT as a postdoctoral associate and research scientist prior to joining Washington University as a assistant professor in 2017. With his expertise in physics-based mathematical modeling and analytical electrochemistry, Dr. Bai has published original research in scientific journals, including Science, Nature Communication, Energy and Environmental Science, Joule, Nanoletters, etc. His contribution earned him the Oronzio and Niccolo De Nora Foundation Young Author Prize from the International Society of Electrochemistry in 2014. By the way, this is a prize awarded to one scientist annually under the age of 30 by ASU. So this is a very prestigious prize. And he also won the ASU prize for electrochemical materials science in 2018. Okay, with that, let's welcome Dr. Bai. The floor is yours.
All right, can you see my screen?
Yeah.
Okay, very good. So let me change to maybe a laser pointer. Yeah, thank you very much for the kind of introduction. I'm very happy today to have the chance to communicate with AI experts to talk about the battery research. I think I checked their series of talks already given to you guys, and this one will be definitely different. It's more like material science, but we really hope that there is a chance that AI can come in to help us understand better the processes. So, as my title said, that we are going to talk about the spatial temporal heterogeneities in battery electrodes. So we will focus on several things, but rather than talk about the physical details of the heterogeneities, we will talk about the consequences when you have this heterogeneities, and that we will show there's a need, we need to handle this and get rid of this from the battery electrodes. So of course, everybody want to have better batteries. For if you ever opened your iPhone or other type of cell phone, you will realize that there is like 1/4 of the weight, total weight, came from the battery. And similarly, if you have an electric car, it also the 1/4 of the total weight and 1/4 of the total cost actually came from the battery pack. And not to mention that one of my favorite robotic humanoid robot, how long it can work depends on the battery. And that battery is in the backpack. It can only serve for 1 hour, but it requires 3 hours of recharge. So that's something we want to change, right? And eventually, talking about, well, lowering the carbon emission, you want to include more renewable energies. Then the question is that for this intermittent power generation, you really need some energy storage method or device that can firm up the energy so that when you don't have the wind, don't have the sunlight, you can use the energy to support your daily life. So here, let's see. This is slide number 3, is that okay? Okay, so talking about the most advanced battery technology, there's no doubt lithium-ion battery is currently most mature and the battery energy technology with the highest energy density. So here I give you a sketch about the internal structure. So basically, it has this kind of a layered structure. You have a copper foil, like a current collector, and then you have graphite particles pasted onto this current collector, serve as an anode. Then you have an electrolyte contained by porous separator. And on the right-hand side, you will have a piece of aluminum foil with some other high voltage intercalation compound being pasted as the cathode, for example, lithium cobalt dioxide or lithium iron phosphate. So you can see here, the reason it is called a lithium ion battery, like the purple spheres I draw here, is that lithium ions will always be in the ionic state. So when the battery is fully charged, all the purple ions will stay in the graphite structure, for example here. But when discharge the battery, the ions then will move out of the graphite, swim across the electrolyte, and intercalate into the cathode material. So you can imagine that at any given time, at any given time point, you will actually have half of the available vacancies still vacant, right? So you're basically waste half of your volume, right? So the idea, and because of this understanding, you can think about that. What if we can remove that volume? One way to do this is to completely remove the graphite electrode and then allow the lithium ion to be reduced into the metallic state, creating a thin layer of lithium metal. So in this case, you save the volume by nearly a half without sacrificing the energy you stored in the system, because all the ions are still in there, well, they can still stay in the cathode and being reduced on the anode. So this sounds like the simplest way to significantly increase the energy density of a battery. But the problem is that when you do this reduction of lithium ions, you're doing this plating or electrodeposition of lithium metal, you will generate this kind of a finger or tree-like structure, and it's called a dendrite. And this dendrite can grow through the nanopores of the separator and give you an internal short. That's not what we want, because batteries then can catch on fire or explode. And on the other side, when we talk about the cathode, many times you see this kind of crystal structure, but that's actually only a teeny part of a nanoparticle. And the nanoparticle is never monodispersed. It will always form these secondary particles. And the secondary particles need to be mixed with other ingredients like polymer binders and the electronic conductive additives to form this composite porous cathode. Okay, so you can see here, naturally you will imagine that when you discharge or charge your battery, how can you make sure every single nanoparticle inside this composite, very complex structure that can give you their performance, right? That can contribute their performance. So here, apparently we have this kind of a multiscale performance problem. So this big picture really defines the research directions in my group. So today I will talk about the spatial-temporal heterogeneities in both the lithium metal anode and also the particulate porous electrode. So for the lithium metal anode, there are some very interesting properties. But if you think about the penetration, there are really two steps. So for example, here, what I show is that we have this already lithium deposition, the purple one. But then when you have this real battery, you have a porous separator. It's inert. It has a pores. Then pores are wetted by the electrolyte. Then you have this kind of heterogeneous interface. But this interface will again already give you some structural heterogeneity. And what happens is that electrodeposition, for some reason, will only take a few pores. And the continued deposition will just place through whatever pathway it can find. And this is something we want to discuss. And eventually short circuit the battery. So there are really two steps. The first step is I'm sorry, my computer stopped working, looks like. Okay, so the first step is really the pore selection dynamics. So why certain pores are being selected for the penetration to continue. And the second is that once you have the penetration being initiated, what is the actual growth process inside that pore, inside that path? This is what we want to discuss today. And on the other side, well, we already showed you that when you have the cathode, you have this many particles being pasted onto a current collector. They actually naturally forms a porous structure. But currently, when people design the battery or considering the safety situations, the most convenient way is actually to use this homogenized model. So just think that everything on this front face, the ABCD plane, is homogeneous. Well, you can model that into a homogeneous way, but the easiest way is that assume that you have the homogeneous distribution. Then you only consider the distribution along the thickness direction. But the problem is that what if particles react one by one, like what I draw here? What if only the right particles matters? Because when you have the full particles, if you have the complete empty particles, they don't contribute to the current you collected. Only the active particles that is really working at that moment contribute to your total current. So here, as you can see that the area of the red particles are definitely different from the area of their square ABCD, right? So it's really just the scientific question is really, what is the true local working current density? All right, so let's talk about the first one. So first of all, what is the lithium metal dendrite? For those haven't handled this, studied this subject, there are several SEM images. You can see here, we have this kind of different forms of fibrous structure. Basically, you have this kind of long, thin fibers that are being called dendrites. Even for this, polymer electrolyte, you see this like a worm-like structure, which is actually not very thick. It's only about 20 micron in diameter. And you would naturally imagine that when you have this fine structure, like a needle-like structure, it doesn't have a chance to pierce through your separator, right? So there is a huge amount of activities, research activities going on, trying to suppress this kind of dendrite growth. And there have already been many successful solutions. For example, here, this is definitely not an exhaustive list. I gave you 3 typical, very famous examples. First approach is basically to change the concentration or change the salt type of the electrolyte. By doing so, you can see that initially you will have this kind of fine structures, but by changing the concentration, changing the salt, you will get some nodal-like structure being more smooth. And the second type is to make an artificial interface, an artificial layer. For example, this kind of layer of a semi-sphere carbons. And this continuous layer can contain this kind of hazardous growth. And the third approach is really to add additives. Here, this work is at adding cesium ions. And you can see here, because it has a different redox potential, it can preferentially being attracted onto the tips of the dendrite, lithium dendrites, so that incoming lithium ions will be diverted to the valleys, so that you eventually, when you compare to the one without additive, the surface becomes more smooth. But the problem is that no matter how you do this, as we already discovered, that if you increase the current density for charging your battery, you will always see penetration. That's very unfortunate. But imagine that in the future, we will have higher energy batteries. At the same time, we still want to charge it very relatively fast. We don't want to compromise, wait for more time, longer time. That means you will have to increase your charging current density. So eventually, penetration can still happen. That's why it is very important that we start to look at the penetration process. So one interesting question, how did this dendrite form? And several years ago, when I was a postdoc, I kind of invented this capillary cell. You can see here, we use just the optical microscope to observe the dynamic process. Here, the difference is that we use a glass capillary and hit it in middle part and pull it further so that we get a very, very thin channel here. And we can push in lithium metal to form the lithium symmetrical cell. The convenience here is that we will be able to see the entire electrode within the field of view. So you won't be able to lose anything, lose any details. So here, you can see here, on the left-hand side, you will see the electrochemical responses. We apply a constant current and we monitor the voltage changes. On the right is the real-time video showing the growth of lithium. So here, because we start from like a 35 minutes, you can see here, we already grow some very nasty structures, very rough structures. But then let me place a video. You can see here, initially, this kind of a mossy structure being pushed forward, right? You can see the tips being, kind of rotate, kind of translate. But when you reach the peak, if you follow the green curve, when you reach the peak, something happens. When you have the voltage divergence, something completely different shoots out, right? And by the classical understanding of metal dendrite, only this part, the fast advancing fractal structure, should be called dendrite. And those mossy structure is actually the collection of whiskers and clustered, mainly controlled by reaction limited mechanism. And only the fast advancing, tip growing, transport limited structure should be called dendrite. But anyway, let's talk about now, how can we understand this, right? So here, this is snapshots of the previous video. You can see here, when you initially have a relatively smooth electrode and you accumulate some rough structure, then current kind of concentrated onto this tip and give you this dendritic fractal structure. And you will have this voltage spike. And this process can be understood very well by classical transport theory for diluted electrolyte. So here, what happens that we cannot see through the images is that we actually have a concentration depletion. The reason is that it's not hard to understand. The reason that when you start to have a negative voltage on the electrode, negative ions will be repelled away from the electrode surface. Positive one will be attracted to the surface, but will be consumed, will be deposited onto the electrode. So the concentration of the salt will have a net decrease. And this process, as you accumulate more, this mossy structure, the positive porous structure, the concentration will keep decreasing. At the moment that the concentration drops to nearly zero, well, the supply is so scarce that you will actually get a blanket of just solvent because you depleted the salt completely. And for this layer of a pure solvent, the conductivity is zero, right? So that you have the voltage diverge, shooting up. And this divergence of voltage will drive the metal to come up, to catch up with the retreating concentration front, which is this kind of dendrite. This is why this dendrite form. And what's even better is that this kind of a time, when you reach when the concentration at the electrode surface becomes zero, something can be calculated very accurately. And it was first derived by Dr. Henry Sally in 1901. And that's why it bears his name, the science time. And it's basically controlled by the system properties and the current density you apply. So here, if we determine, if we read the time, when we see this kind of transition of growth, the dendrite initiation and the voltage spike, we can vary the current density to find the series of the dots. And it's just as the science time formula predicted, it followed the power law, right? So on this logarithm plot, it falls on a slope, straight line, a straight slope. And what I didn't mention is that there is one premise that you must meet, which is that you need to use a high current. But how high is high? So one very important concept here is the limiting current. So limiting current, again, is a system property, but it depends on the L, and L is the distance between the two electrodes. So here you can see that for our capillary cells, we have a separation between two electrodes around 5 millimeter. That means you will have a limiting current to be 1 milliamp per centimeter square, right? So that's why even if we use like a little bit above, the current density a little bit above 1 milliamp per centimeter square, you will see this kind of sense time. You will generate diffusion limitation. But in reality, when you have a coin cell, when electrode distance is around 100 micron or even smaller, you will have a limiting current larger, near or closer and larger to 50 milliamp per centimeter squared. So that basically tells us that in reality, you should not have tip-going dendrites in your battery. It won't occur because you won't reach that high current density to trigger diffusion limitation. But then what's very unfortunate is that penetration still occur, right? You won't be able to generate those structure that can go through the separator, but still penetration happened. And not only that, when you look at the slope, it's not a strictly -2, not only for the capillary cell, but also for many other practical coin cells. People always find this minus 1.5, 1.4 slope. What's the reason of that? So there's really two questions we need to handle. First, why penetration still happen when the current is lower than the limiting current? Now the second is that when this penetration happen, why the characteristic time versus current density give you an exponent larger than -2. So the first thing is that we want to understand a little better. So we kind of put a lot of separators between two electrodes to run some abusive test to see what is the penetration process. So as you can see here, from near the anode to away to the cathode, we have this kind of a piece of a separator. You can see that the black area is actually where penetration happened. But you can see here the collective area is actually reducing from 1 to 5, so from 5 to 10. And if you characterize the area, the penetration area on the final separator, it's actually very small, right? It occupies a teeny portion of the total geometric area. And this is not only true for our commercial separator. It also happens for glass fiber separators. You can see here for this very large glass separator, you only have a little black dot. This is the dendrite penetration. Well, it may not be dendrite. It is the metal penetration. And this also happened for ceramic solid electrolyte. Okay, you can see here for this very large pellet, only a few dots. You can see the penetration. And also something observed in polymer electrolyte. So everywhere, whatever kind of a separator with the liquid electrolyte or solid electrolytes pellets or films, you always see this penetration happen locally. So then if you quantify the areas, you can see that the penetration area versus the geometric area is very, very small. That means you have a very large amplification factor or current focusing effect here. And when that happens, the local current density easily exceed the diffusion limitation. That means if you calculate by using your electrode area, okay, that's a safely designed. It's a current density that will never reach the diffusion limitation. But when penetration starts to occur, when you go inside a separator to just a few pores, the local current then is very, very strong. Okay, so that easily go beyond diffusion limitation and it can trigger dendrite growth. And then you can see this explains why we have the controversy introduced earlier that penetration happens locally. But then the second point is that if you pay attention to the collective area, you can see here, the area is reducing. That means along the penetration path, there is a geometric change, right? There is a geometric change. So this is really the first time we're thinking about, maybe it's time to really talk about the geometric effect. And the one way to do this is to go back to check our capillary cell to see whether the non-ideal exponent came from the curved structure. So when my student Bian Ma tried to study the sodium electrolyte system, the sodium metal system, he found out that, well, you can actually, because of electrolyte, you can push the metal right to the middle part so that it's almost straight. And well, if you change it to another electrolyte, you can actually only push to the tapering part so that we got two types of geometry. One is the straight channel, the other one is the curved channel. So this is the way we started the geometric effect. And based on that, Yunzhi Li carried a systematic study to verify our hypothesis. So I will introduce now our discovery. So you can see here, for the straight channel, surprisingly, again, each dot here on this chart, on this log plot, came from a single experiment using a different current density track where the voltage diverge, track where you see the transition of metal growth. And surprisingly, you can see now for the relatively straight channel, we did got a slope very close to the ideal case. In contrast, that if we leave the electrode to this tapering part, meaning that it will grow along a channel where the cross-sectional area is continuously reducing, it's converging channel here, then you can see that as we obtained earlier, we got a slope to minus 1.45. Away from the ideal exponent, we have a positive deviation. So this is confirmed us that there is indeed a geometric effect. And what's surprising though is that visually, you would see that this kind of change of curvature is very tiny, right? So that means the transport dynamics, the penetration process is very sensitive to the geometry, So here, we further tested that if we push the metal electrode to this part, to the other end of the tapering part, so that we have an expanding channel, what will happen? And this is what happened. Not only that, we no longer have like the slowly climbing voltage than the divergence, but we have a decaying voltage, then the divergence of the voltage. And what's more surprising is that now we have a slope with a negatively deviated exponent. You can see here, -4. Initially, ideal case is -2. Now we got a -4. So what's the significance of this? The significance is that when you have this negative deviation, you actually will increase your system-specific limiting current by orders of magnitude. So here, for this case, for our regular capillary cell, going beyond 1 milliamp per centimeter square, you can trigger diffusion limitation. But if you have the expanding channel, you have to go beyond you can see here, you have to go even beyond 75 milliamp per centimeter square to really see a clear transition for growth, to see the depletion of concentration, to see the diffusion limitation. So that tells us maybe we can engineer some structure so that along the penetration path, you will go back, you will degrade back to some safe current density. So here, before we go into that part, we kind of explore, the human intelligence to say whether this is really theoretically, physically possible, whether our observation is not an artifact. So this process can be very well modeled by this effective electrodiffusion equation. But when you consider the varying cross-sectional area, you will have this additional term. So this equation, by just looking at it, you don't think there is any analytical solutions. But what if we, look at this structure. There is some kind of the first order derivative divided by itself. Well, it reminds us, what if we can approximate it by some exponential equation? Then if that's true, then this term can reduce the scalar. And this function becomes a very general, the simplest reaction diffusion equation, which can be solved analytically. So we did this. For different types of capillaries, we can use this exponential equation to approximate the area change pretty closely. And you can see that we were able to really find out an implicit but analytical sense-time formula. And then on this chart, you can see that indeed depends on the conversion rate of your channel. You will get positively deviated exponent or negatively deviated exponent. So that gives us the confidence that you really can rely on the structure, just a static structure. If it can promote some transfer, beneficial transfer process, it can change the dynamic metal penetration process. So here, let's come back to what we did with the multiple separators. If you really quantify the dark area for each separator, you can see that we effectively form a converging channel, right, along the depth direction. But what if we can promote the lateral transport so that the penetration will grow like this? You will have more pores being filled with this metal penetration, but eventually you will result in a much lower current density so that you will never trigger diffusion limitation. So this is actually currently the question lead our current research. So basically, there are several scientific questions. The first one is that how were certain pores selected at the interface at the very beginning, right? And that why did the penetration area shrink for this particular case and for many existing cases? Why do we always see this positively deviated exponent in realistic batteries? And then if you think about the microstructure of the separator, when metal tips going through the pores, how did the growing metal tips choose their path? Why did they converge instead of expand? Then the final question is that what types of microstructure can enable effectively the expanding channels like I draw here, indicated here. So I think especially for the last three questions here, I think this is the AI that really can come in to help us to help design the optimal structure of the separator. So as a quick summary of this part, I hope you guys now realize that metal penetration occurs locally, as we already showed that. And when penetration starts to happen, before you have the eventual short circuiting, the enabling current density for that local region is several orders of magnitude higher than the safe current density designed by existing models, right? Because they handle the homogeneous situation. then to optimize the heterogeneous microstructure of the separator, and if we can promote the lateral transport, and we may eventually retard or even avoid completely the metal penetration. Okay, so I think maybe I just pause here to take some questions.
Yeah, sure. I have a question. This is amazing. Can you um guide us through the thought process where you identify the geometry actually matters? I think you talk about it, but I want to just think about it again.
Can you say that again? So,
Oh, can you hear me?
yeah.
Yeah, I said, can you guide us through the thought process where you identify the when you identify that the geometry actually matters in this
Yes,
dynamics? Yeah.
yes, definitely. So I think let me go back to the to this result. So basically, you can see here that we have two types of channels. So the reason we use a channel instead of using some more realistic setup is because you really don't have other more reliable method to probe this problem. And this is the first thing, just to talk about the geometric effect. So here, if we have a straight channel, that means that you don't have a geometric variation along your penetration path. Then you got something ideal, meaning that the exponent here, minus 1.92, very close to the theoretic prediction minus 2. That means there is no geometric effect because the theory didn't consider any geometric effect. And you match that. But then when you have this curved channel, it deviates from the theoretical prediction.
Right. I can see that. I guess the more of a question or curiosity is if you go one slide back, and another slide, I guess there's an experiment. Yeah. So this one here, when you look at these images from 1 to 10, right? I think you realize that, oh, maybe geometry matters.
Yes.
How does, I think there's a jump here in logic. Can you explain why or how you realize that the geometry actually matters by looking at this experimental
Oh, yeah.
result?
Okay. So here, I think we didn't try to we didn't reconstruct the structure, but if you can flip up every separator and line up layer by layer, right? And for the first layer, you have many more penetrations. And when you go to the second layer, the area reduced. When you go to the third, it reduced even more. And then go to the final, you only have a little point. So collectively, you can think of that for whatever reason, the penetration structure kind of converge, right? That itself is a geometry. It's not a straight geometry, it's a curved converging geometry.
Okay, so if so that means that if the chemistry here, I will just use very loose words, is independent from the geometry, then what you should observe is that you have basically constant pattern from 1 to 10. Is that right?
Yeah, that's our expectation, and that's what we at least
Okay.
what we want to achieve. And I think ideally is that we will have this kind of expanding conduction channel so that the penetration won't even happen, because penetration, when they try to happen, it always expand. When you expand it, you lower your current density. So when you lower the current density, you will not be able to grow further.
Mm-hmm.
So that's why it's because of this kind of a collective effective geometry. We think that, well, it's not exactly matching our capillary cell, but there is a geometric effect.
Mm-hmm. I see. Yeah. Thank you.
All right, so maybe I continue discussion on the other electrode. So here, as I said, that we also study the basically the cathode part. Cathode will always, for lithium systems, cathode will always be porous, containing many particles. So here, the first slide basically show everybody that this is not something I make up. Okay, so the heterogeneities actually did exist, and we have this particle by particle heterogeneities, and even within single particle. Okay, so there is heterogeneous, but only being appreciated in recent years. Before, people would rather just believe this is relatively homogeneous. It's not a problem, but it's getting more and more attention that heterogeneities play an important role, especially for the degradation and the safety of batteries. So here, when you see this kind of contour, different color and heat maps here, it tells you the level of heterogeneity. And the consequences are many, many consequences. So first, practically, you would easily imagine there are hot and cold spots, right? When you have the hot spots, of course, they can really become hot spots because the pass a higher current. And their Joule heating effect, the local heat can even melt your polymer separator, right? That's really a safety threat. But when you have a cold spots, that means, okay, some amount of a material did not participate in the reaction. So you waste the material, you're compromising your energy density. That's not what we want, right? But more fundamentally, the question is, which parts carry the reaction current, right? And when you design your battery, should you use the total current or should you use the local current density? The answer is obvious, right? We should use the local current. We should use the working current density. And this is more fundamental for electrochemical characterization, because always the most important parameter we need to identify is the diffusion coefficient of lithium into the solid material. And it has this kind of a square law dependence. It depends on the current density squared. And current density, of course, the total current divided by area. If you have an error in your area, you will magnify the discrepancies here, right? So, for example, this is again something already existed in the community, in the literature for many, many years. For different type of material, there are always several orders of magnitude variation for the characterized diffusion coefficient. And even more recently, that the micron size, the single particle solid solution material, nickel manganese cobalt oxide 333, is determined to be not diffusion limited, right? It's not limited by solid state lithium ion diffusion. Can you imagine that? It's hard to imagine because everybody would think that you have ions diffuse through solid, it should be really, really slow instead of a reaction on the surface. But this really matters because it changes the strategy. You optimize your battery. If it is diffusion limited, okay, you reduce your size of particles, right? But if it's a reaction limited, then you should just create a better surface coating or just maximize the most reactive facet of that crystal, right? But it always rely on an accurate determination of the diffusion coefficient, which then rely on the accurate determination of the active area, right? So this is why we are focusing on this heterogeneities. So here, this is what my student Shobhan did. And we spent quite a long time to figure out the best configuration to characterize this graphite electrode. So in the middle, you can see here is a black electrode. It's black because it's graphite. It's the same material used in our pencil. But you can also see this gold stuff is not because we have some dust or something or gold coating. It's because when lithium when lithium goes into the graphite can change color. So let me now play the video. So you can see here, we're doing a so-called PITT experiment, potential static intermittent titration technique, PITT. So simply speaking, it's just a series of voltage steps. So you can see here, initially the black particle turned blue. Then now, to the final step, you can see here, it turned red. And while we are holding the voltage there, it further turns gold. So there is actually phase transformation. There is phase transformation from a blue to red, from a red to gold, when lithium goes into the graphite particle. So here, because of this special property, we were able to characterize what is the actual area carried by each color or carried by each phase. So here, so what Shubham did is that we convert the different colors into the standard RGB for easier analysis of the area evolution. So the blue was converted to blue, red to red, but gold to green. So you can see here, this now the purely the experimental result. We use image J to characterize the area fraction of the blue. And you can see here, starting from the blue, when red start to emerge, blue quickly drops. But the gold is kind of relatively stable there, waiting for the red to reach the maximum, to basically waiting for the entire electrode to become red, so that the gold color or the gold phase, which is the stage one, by the definition for graphite phase transformation, start to occur. Okay, so we have this kind of a mutually exclusive sequential process, blue to red, red to gold. And then if you just use this image, because each color represents a phase. Phase means stable composition. It has a stable stoichiometric ratio of lithium ions inside, or mole fraction of lithium inside. So you can actually convert the color into charge. Then if you take a time derivative of the charge, you will get this current. So you will get the current carried by each color or carried by each phase. So what's already surprising is that you can see here, the dashed line is the total current you collected. But looking at the detail, looking at the microscopic evolution, the current density, not even the current density, is much higher. Or at least it's totally different. It's totally different. So then we went on to do more detailed analysis. So here, if you look at a single particle here, you can see that from complete blue, you will nucleate some red phases, which is the stage 2, and create this kind of a phase boundary propagating through the particle and make the, so here you can see that the phase boundary not only propagate, it kind of evolve so that eventually the particle becomes totally red. Then after that, you will see this nucleation of gold phases creating new phase boundaries, right? Then eventually sweep out the entire particle. So if you do this carefully enough and adopt some Boolean operation, you can see that we can actually characterize the evolution of the interface length. And for the interface between the blue and the red, it looks like this, non-monotonic behavior. For the red to gold transition, again, non-monotonic behavior. That when you know the interface length, you know the thickness of the particle, you can calculate what is the actual interfacial area responsible for this kind of reaction, right? So that you can calculate the true local and working current density. So again, you can see here, this is roughly 1 milliamp per cent squared compared to the geometrically average current, well, average to all the available surface area of the particle is almost 3 order magnitude, 3 order of magnitude higher, right? So you have to use this true local current density to estimate, to characterize, or to evaluate the electrochemical processes. So to do this, so here, the red one, these two figures are really just came from the interface we characterize. You can see here, we develop a model showing up here that can accurately fit the curves. And it actually based on the very famous, widely used the growth theory. But there are differences. And the general growth theory can definitely fit the curve, but you cannot expand the parameters. Well, to make any fitting physically reasonable, you always have to go back to the parameter to see what is going on with that. So here, let me explain our model a little bit. Not the derivation, but the parameters. So here we really have just 3 parameters here. The right one, the n, is a dimension, is a dimension exponent. For this case, we are studying a 2D process, so it should really be 2. But you can see here for different experiment, we really got something close to, especially with 200 millivolt steps. It's very close to 2. But we also consider there are inaccuracy when we characterize the color areas, and there are variance of the thickness of the particles. So this is acceptable. But the S here, because we're analyzing the length of the interface, not the direct area, but we have to adopt one shape factor. So here, what I can tell you is that if S equal to square root of pi, that means you will have a perfectly radial or a perfect isotropic or perfectly circular growth. And square root of pi is 1.77. So here you can see here, even though it's not 1.77, it's very close. And because we already also see relatively isotropic, locally isotropic growth. Now, eventually the rate K, and this K is nothing but the propagation speed of the interface. You can see here, this is what we fitted. And this is something directly characterized from the reading the operando experiment of a single particle. They're very close. They are very, very close. Not only for the blue to red transition, but also the red to gold transition. Okay, so I want to use this slide to summarize this part. So here you can see that we did a lot of things. And this is really the very comprehensive electrochemical characterizations from every possible aspect. But you can just believe me that we got a very reliable result. That's all you need to assume now. But there are several surprising conclusions. First one is that by looking at the top row, this is the current versus the reciprocal of the square root of t. The reason for this kind of a special arrangement is because the way to analyze this current density, if you believe that's a diffusion limited case, you should use cultural equation. Cultural equation gave you this relationship. But when you have this plot, if it indeed follow the cultural process, a diffusion limited process, you should have straight lines. But as you can see here, we don't have straight lines. So that means it's not diffusion limited. But what's even more surprising is that it's not reaction limited either. Because look at this 2 panel here. You would imagine for any electrochemical reaction, when you have a higher voltage, the reaction should go faster. You should get higher current density. But guess what we did? What we obtained? When you have a larger voltage step, 200 millivolt, the local current density becomes lower than the 100 millivolt excitation. How would that be possible? Same thing here. When you have a larger excitation, the resulting current density is even lower than the lowest excitation, smallest excitation. So higher driving force leads to lower true local current density. Why? It's actually not hard to be understood because there are two effects of the excitation of the driving force. Here, it simply activated more particles. So the total current being distributed to more particles, yielding a much lower true local current density. So that's why our conclusion here is that the process is really not diffusion controlled or limited, not a reaction controlled. It's really just the phase transformation controlled because it affects the two levels of processes. The first level is how many particles you can activate. You can trigger them to participate into the reaction. And the second level is that this excitation will also control the phase boundary propagation within each particle. So that is why we should really call it phase transformation controlled. Then the question is that, and this is actually what we are currently pursuing, is that can we identify or establish a clear correlation between the excitation? We have a different current density, we have different voltage steps, and between this excitation and the population. When you have a different excitation, you have a different population of particles, either different shape or different size or different locations. If we can identify this correlation, then we can generate an optimal protocol. For example, when you want to drive the battery very hard for acceleration of your vehicle, you imagine that the high current will generate a lot of particles. Then you will, design your battery to maximize that population, right? That best suited for sports cars. But if you're considering a golf ball car, then you can consider, well, maybe we should use another type of set of particles that just fulfill this kind of a task. So this is something we hope AI can come in to help establish, because we can do the full scale simulation, well, create a batch of 200 particles, simulate at what kind of situation you promote what types of particles. But when you talk about a real battery containing billions of particles in each electrode, AI should really come in to help us. All right, with that, I want to share with you this kind of a take-home information. So the first thing is that I hope you already realize that the spatiotemporal heterogeneity is not only real, they will lead to extremely high local current densities for both the metal anode and the porous electrode. Okay, so we should really focusing on local, not only local, but also the truly working current density. That's for that we call it operando current density. And more specific for the metal electrode, we hope that AI can come in to figure out what is the optimal, this multiscale structure of the separator that can enable expanding penetration channel or conduction channels or structures so that we can retard or avoid the dendrite penetration. And for the porous electrode part, I think there is really a good chance that AI can help us identify what is the optimal charging or discharging protocol that to activate the right amount or right population of particles. Okay, with that, I'd like to thank my students, Yunji Li, Bingyama, and Shubham Agravel, and they worked really hard, to try this challenging ideas and then make this, obtain this beautiful results. And our work presented here was supported by NSF, a grant, and also several internal supports. All right, and now I'd be happy to take any questions. Thank you, guys.
Oh, this is a fascinating talk. Let's first have a couple of questions from the audience.
Sure.
By the way, I see Dr. Yang Zhao here. He's the PI of the AI Institute Planning project. Yang, do you want to talk about something? You have some comment on this?
Sure. This is a very interesting talk. Actually, I have a lot of questions, but it's from the audience, and then I can go ahead and ask.
But you're also part of the audience.
Okay. Okay, sure. So this is a very interesting talk, actually. And yeah. So, and we actually did a lot of modeling aspect. I think that in this work, you mainly focus on the nice experimental work that I have done, but we actually done a lot of modeling aspect that's quite relevant to the systems they're looking at. And from the intro page, I think it's page 16 that you show to the schematics. So from what I see here is that the overall theme of this AI institute is actually to use the smart AI research to add material science and engineering. And the basic idea is that a fundamental principle for us to derive AI frameworks that help us to better understand how material work and to make predictions for the better design of material is based on the fundamental relation of structural property. So basically what we consider is that, whatever material, whatever functionality and property is interested, you have to go back to the actual microstructure of the material and the associated physical mechanisms and equations. So based on this, the idea is that we can also revolutionize the current way how people model material, use individual numerical schemes and explicit equations to completely different way of looking at the system. For example, if we consider a material is a network, have a hierarchical of different microstructures on different levels, starting from the most fundamental atomic level, and all these atoms are kind of connected to one another through bound, right? And this information is given to higher level scales, to dislocation level, to this microstructural level, and depending on what physical processes are interested in, different bounds and connections can be activated. If you think about it, this is more like a huge network.
Yes,
right?
Exactly. Totally agree.
Yeah. So what we do is that we need to find a feasible. That's basically the underlying reasoning. So what we need to do is that we need to find some feasible mathematical structure for this network, right? Because material contains at least of atoms. That is a large number, and there's no way that you can handle this network in any computational resource. So the idea is that we have to define this in a very the node that representing the microstructural features of interest. And secondly is to make connections to build a network, right? Connecting these nodes. So those are very simple ideas, but technically there are a lot of things that we need to figure out. But anyway, so that's the basic idea of the this AI MSE Institute. But to do that, I think the first step is need to really find very nice nodes, right, in the network, for example, to represent your microstructure. And we know that if you're in different physical problems, the different levels of microstructure are going to play a role. And in here, I think you show at least the two different microstructure models from my perspective. The first one is that we'll study the least subtle dendritic growth, and we talk about this porous electrolyte. We actually did a lot of interesting and similar work to quantify the porous microstructure. And in fact, Max is currently working, we've worked together on a project that we develop these, what we call the higher order statistical vectors to quantify and reconstruct very complex porous microstructure. And based on these descriptor quantifiers, we can make predictive modeling of the material properties. So maybe we can have a separate discussion later, but just the similarity and synergy that I see here. And for this electro modeling, especially the packing model, we also did a lot of work in this aspect. I think here what you showed we call a polysphere packing model. And from the red, what I can see here is potentially a percolation pathway by these particles. And we have a lot of powerful mathematical and computational tools to look into the structural complexity and see how that is correlated with the the experimental results that you have obtained. And I think all of these are, I think, very good starting point to build some neural network model that can potentially be able to I would not say help to design, but at least characterize or at least help to model the system you're looking at. So these are my general comments, and that I see how your next work can fit into the AI Material Science Engineering Institute that we're currently building. So
yeah, thank you very much for the comment. I totally agree with you, and these are your comments are really music to my ears, because many times initially we would push ourselves to the limit that we would just want to see how human intelligence can reach. So we think very hard to handle this kind of a single particle physics and the interaction between several or at most 200 particles. But then if you calculate just in our cell phone battery, there are billions of particles there, you feel, well, this is really something we need to explore. Artificial intelligence tell us what is the what is the result that has the statistical significance, and maybe there is some kind of a pattern, reaction pattern or degradation pattern that cannot be revealed by looking at just the 200 particles, and we really need another level of tools or methods to help us have a more accurate understanding. There are currently, AI deep learning results of the battery research, many, but I think there is still a lot of opportunities to really still connect the true physics with this AI predictions, and not only just to tell people what is the correlation, but also what is the physical reason behind this correlation. I think that's something we can come in to help to get it to kind of complete the picture.
Yes, I totally agree with that. This is totally aligned with our ideas, because we're not just using this as a tool to fit the data, but rather we're building a new structure using the network, right, to describe the physics of the system.
Right. Exactly.
So yeah, but I think the key really is that if you want to capture the fundamental architecture of your network, it should actually reflect the architecture of the physics. That's exactly what I think materials is a good system for us to do so, because it's natural to define the nodes as different levels of microstructure features. And the other interesting comment you just mentioned is that you said that maybe we can monitor 20 particles. Happens if you're just applied this knowledge to the actual battery, which have millions of particles. This is also very interesting because we are actually, at least I hope that eventually we can reach this goal that we're building a physics-based learning architecture that can eventually capture all of this emerging physics. You actually study these individual pieces together, but when you put there, you can actually the network or this architecture will be able to what are the new emerging properties that are resulting from these individual pieces. I don't think we have a full picture of how to do this, but we have some ideas of how we could possibly do this, like using neural graphs and neural OD that combine with these nice experimental results and simulations. So this is very interesting. So I still have some questions, but I think maybe we can ask any others from other audience.
Yeah, although we have passed 1 hour mark, but if you have questions, please go ahead.
So I have a question here. So for the particle system, what specific particle system you are referring to, the NMC 333 or any other?
So here, basically, we are working on, we're using, so currently the result I showed today are graphite particles.
Okay.
So here, yeah, there are graphite. The reason is that only graphite has this optical property, so that we can do this by using just the regular optical microscope. We don't have to go to the national level facility to use the synchrotron X-ray. So here you can see here, this is the first one is graphite. This is every lab can do, although there is some know-hows you need to figure out, but it's very easily accessible. All the other things require synchrotron X-ray. So that's why we choose graphite as a starting point. But we are also, graphite is not only a very important electrode used by basically all the lithium-ion batteries for cell phones, for laptops, but it also represents one type of battery material that is a phase transformation materials. So it's very representative for lithium iron phosphate, for many other different phase transformation materials. And the second type, as you mentioned, it could be NMC 333, but it could be NCA, nickel cobalt aluminum, and it could be NMC 811. To us, it's really not too much different because they fall into the same category. That is the solid solution battery materials. So we are currently using NMC 532 to characterize their heterogeneity by using Raman spectroscopy, and for which we didn't show the result here, but still we saw similar kind of heterogeneity map, and we are
okay.
Yeah.
Okay, so so in terms of phase transformation you just mentioned, so does the NMC 333 has the same phenomenon?
Well, they have some irreversible phase transformation that cause capacity loss. So when I say that the phase transformation electron, we mean that it's a reversible phase transformation. So that basically whenever you look at the voltage profile, you have a constant current discharge, you look at the voltage. Whenever you see this flat voltage plateau, that means 99% chance that you will be correct. That means it's a phase transformation material. Solid solution material, on the other hand, actually got this kind of sloped or tilted voltage plateau, or even probably don't even have a voltage plateau. And that's the major difference in terms of performance. So we don't consider the solid solution material has phase transformation, reversible phase transformation behavior.
Okay, so yeah, as far as I know, like for NMC 333, it's like during the charging and on charging, like you have large volume expansion, like the ratio is very large, then you will see severe fracture. I mean, maybe within the particle or between the particles. So did you observe the same like for the graphite material you just talked about?
Well, yes. So graphite can also have, depends on what kind of ion you accommodate. It can also have expansion, but for lithium ions, there is only 6 to 10% of volume expansion. So it's not huge. There definitely is, because if you look closely under the microscope, some part of the electrode can become off focus, but not severe.
Okay.
And
okay,
yeah, same thing also applies to this kind of a very mature cathode materials. There is volume expansion, and in some papers you can even see the cracks being developed. But that happens only after many cycles. And for our experiment, we are focusing more like in the very initial processes. We have another project trying to test what is the long-term effect after many cycles. What's the effect? But if you consider only a few cycles, the crack won't be a problem.
Okay, thank you.
Yeah, you're welcome.
So before we wrap up, can I still have one question?
Sure.
So for the second part of the talk, I think there's one slide where you propose one model which combines the polynomial term with exponential term. I cannot name it.
Yeah, there is
So-
no polynomial term. It's just the. Oh, you mean the multiplication of the t?
yeah.
Okay.
Yeah. So for this model, can you? I think you already explained it, but
No, well, that's a good catch. I didn't explain how we achieve this. And,
right. That's what I'm curious about. How do you come up with such a model?
Yeah. So, I always kind of boast to my students that if you give me 4 parameters, I can fit whatever curve you gave me. And the only, trick is that you need to know what is the function, right? So here we have an exponential function, and within the exponential, we even have raise the term to the nth power, right? So it's not trivial, and but it actually we didn't just came up with this from nowhere. It's actually based on the classical growth theory and called the KJMA theory, or in US is more popular to name it GMAC. Anyway, it basically says that it's actually depicted here is that if you consider this is well, let's don't talk about the interface. Let's just talk about the area. You will have nucleation in this domain, right? And when the nucleation grows large enough, you will have impingement. Let's just for one time instant, let's hold this small particle static, and let just a larger one grow a little bit, give you this kind of a differential increase. Then you have 2 parts of this ring. The entire ring, of course, there's something very easy to compute, to characterize, because that's just a ring, a perfect ring. But the actual growth, that how much new material being transformed is this broken ring, dA, the actual growth. But imagine that you're throwing it's basically statistics that the chance for this entire ring, that the chance that this much will fall into the untransformed part, basically the ratio between dA and the dA extent equals the fraction untransformed part of your system. And that is how that's the differential kinetics we based on. And from there, we can eventually derive this equation. Yeah, if you're interested, I can explain more, and you're also welcome to check our paper. It's available on archive.
Yeah, this is really great. I ask these questions because I feel that these are the things that's missing in our current framework. So right now, I think Dr. Zhao explained the big picture, and I would say it is I would call it AI for computation. And we're not reaching AI for science yet. I understand that, by discovering these equations or the geometric dependency, like in the first part of the talk, this is actually rewarding as a human scientist. Maybe this is something that we don't want to take away by AI, but we keep on having what we're trying to push forward is to go from these let's say neural architecture search, which is still very computation based, to AI for real science, right? But we can have a offline discussion about that.
Yeah.
Okay. Okay, with that, let's thank Dr. Bai again and wrap up the talk. Thank you, guys.